On the ability of neural nets to express distributions, this is joint work with Ranga, Tengyu Ma, Andrei Ristevsky, and Sanjeev Arora. Okay, and the slides and paper are available at tiny.cc/hl-colt17. So first, an introduction to the problem. We all know that deep neural networks can compute very complex functions. But another recent use of neural networks has been as generative models for complex distributions, such as natural images, handwritten characters, or speech. And so these networks, which include the popular generative adversarial networks, when trained, they can take IID, random noise, put it through the neural network, and put out a realistic distribution of images. So given the success of these networks, we can ask, why are deep neural networks so effective at generating many distributions that occur in nature? Our main results are twofold. First, we give a Fourier criteria for when a function can be represented or approximated by a L-layer neural network. Roughly, our result says that a composition of L barren functions corresponds to a L+1 layer neural network. And I'll describe exactly what I mean by a barren function a little bit later. As a corollary of this, we get a theorem that says when a distribution can be represented by a L-layer neural network. Our second result is a separation result that gives a function that is a composition of barren functions, but it's not a barren function itself. Think of this as analogous to a separation between 2- and 3-layer neural networks. Okay, in order to give the setup for our theorem, I'll first describe a classical result known as Barron's theorem that we build off of. First, our setup. We will be considering feed-forward neural networks with L hidden layers or L+1 layers in total. The way these networks work is at each layer you compute a linear transformation followed by a sigmoid nonlinearity, except at the last layer where there's no sigmoid. Here, a sigmoid nonlinearity is any continuous function that goes to 0 at negative infinity and 1 at positive infinity. I also mentioned that our results also work for ReLU activations because you could sum two ReLUs going in opposite directions and they'll form a sigmoid under these definitions. Okay, Barron's theorem says the following. I'll restrict to the unit ball, even though the results can be stated more generally for other bounded sets. So suppose mu is any probability measure on the unit ball in n dimensions, and the Barron constant of f is c sub f. Then f is approximable by a 2-layer neural network with on the order of cf squared over epsilon squared hidden nodes in L2 error epsilon. Okay, so I will need to tell you what the Barron constant means. So here's a cartoon picture. So roughly speaking, the Barron constant measures in how many different directions the given function varies in. So if we look at the left-hand side, we see a function that is a sum of two functions which each only vary in one direction. This means that the Fourier transform of f is going to be supported solely on those two directions. And the Barron constant Cf is going to be small. On the right-hand side, we have a function which varies in all different directions. The Fourier transform of f will be supported in all different directions, and the Barron constant Cf will be large. Okay, so more formally speaking, the Barron constant is defined as the infimum over all extensions big F of f that agree with little f on the ball, of the integral of the norm of omega times the norm of the Fourier transform of f of omega. And using some Fourier analysis, another way to write this is as the norm of the Fourier transform of the gradient of f. Okay, so from this you can see that the Barron constant is kind of like a L1 norm. This means that bounding the Barron constant will be like instead of bounding the sparsity of the directions of variations, we bound some kind of L1 relaxation of that. Okay, so I'll give a very quick proof sketch of Barron's theorem so you have an idea of why it's true. So the first part is to write our function f as some combination of sigmoid functions. First of all, at first not caring about how many sigmoids we use. And we do this in 3 steps, writing first as a combination of sinusoids, then as a combination of step functions, and finally as sigmoids. So to write f as a combination of sinusoids, we can use the inverse Fourier transform formula and some algebraic manipulation to get the equation printed. Then we have these sinusoids, which we write as a combination of step functions using the kind of technique given in the picture, where the total sum of coefficients of the step functions that we use will be bounded in terms of the amplitude of the sinusoid. And finally, we can write a step function as a limit of sigmoid functions. So this shows that if we have bounded Barron constant, we can write it in terms of these sigmoid functions with the sum of coefficients not too large. And finally, we use the sampling trick, which is we have f as a linear combination. Now we sample according to the size of the coefficients. And then we get a representation using only R terms, and the error we get is bounded by Chebyshev's inequality. Okay, so now I can introduce our result. Our first main result is on representation. So we say that this Barron's theorem generalizes in a natural way to L layers. It composes. So here's the setup. We have mu0 distribution on the unit ball in m0 directions. If f is a composition of L different Barron functions, say with Barron constant Ci, then we can approximate f by a neural network with L plus 1 layers, with parameter polynomial number of nodes, and all these parameters. Okay, so there's some technical conditions here. First, each of the FIs have to be Lipschitz, and actually we require that the functions FI not just to be Barron on the ball, but on an expanded version of the ball, say 2 times the unit ball. Okay, so what does this theorem tell us about approximating distributions? We have that consider that we start with IID noise, say, and then nature applies some function f, which is a composition of Barron functions, and gets a distribution. And we get a function g from our neural network when we also apply it to this random noise to get another distribution. So we have that the appropriate distance between these 2 distributions is small, and the appropriate distance here is the Wasserstein distance. The corollary of this is that no one Lipschitz discriminator can distinguish between these 2 distributions with advantage greater than this quantity.
How do you define the L2 Wasserstein?
So think about it. I don't have time to go through the...
The question is because you're talking about Lipschitz functions, but L2 Wasserstein distance is typically the expected value of the squared norm.
Yes, that's right. There's a Cauchy-Schwarz inequality involved.
You mean that you look at just the expectation of just the L2 norm of the square or the square of the L2 norm?
The expectation of the squared.
Do you want to take questions?
Okay, we can talk more offline.
This is unclear.
Okay. Okay, so the proof of this result is we take our functions fi, and for each of them we can apply Barron's theorem and get a neural network with 1 hidden layer. And we notice that from composing these, we get a neural network with L hidden layers. And note that the layers in the middle only have linear functions, so we can collapse them and just get the L hidden layers. Okay, so to make this technical, we want to induct on the number of layers L. And what we actually do is we restrict to some set SL, which contains most of the probability mass. On the induction step, we use Barron's theorem for the Lth layer and the triangle inequality. And the key here is that Barron's theorem works for any distribution. Finally, we bound the error naively on the complement of the set SL. Okay, so here's the same proof in pictures. So we use the triangle inequality at each step, and we use Barron's theorem for the lth layer, noting that the distribution we use is going to be the push forward of the base distribution mu0 by the previous L-1 layers. Okay, so for the theorem for distributions, here's the corollary again. And what I mean by a discriminator is a function that gets access either to the real distribution that's generated by f, or the distribution generated by the neural net, which is generated by g, and wants to make this difference as large as possible. And here you can bound it by the Lipschitz constant times the L1 norm, which you could bound using Cauchy-Schwarz by the L2 norm. So this says that the discrimination ability is bounded by the error in function approximation, which we already calculated. Okay. But we can ask, is this theorem a non-vacuous statement? That is, we said something about compositions of Barron functions, but do composition of Barron functions, are they a larger class than just Barron functions? And the answer is yes, which brings us to our next result on separation. Okay, so our main theorem here is that there exists a function f from Rn to R such that f is not Barron with a polynomial constant, but f is a composition of two functions with polynomial Barron constant. Okay, and note that this is analogous but technically incomparable to a separation between 2 and 3 layer neural networks. Okay, so the function f that we will choose for this separation is going to be a radial function, f1 of the norm of x, and it's going to look like this, be a ring that's peaked at some radius. So why is this a good choice for our f? Well, first we have that because f is a radial function, the Fourier transform of f is also a radial function. That means if we choose f to be steep enough, then this integral that appears in the Barron constant is going to be large. And the second part is that it is a composition of two Barron functions, namely the norm squared of x and the function from y to f1 of square root of y. The first function is the sum of xi squared, and each xi is a projection onto one coordinate. So this varies in few directions. It's a Barron function. For the second one, we note that any smooth enough one-dimensional function is Barron because there's only one dimension to vary it. However, there's a problem with this proof sketch, and it's that we need to bound this integral not just for f, but over all extensions, big F of f, little f, that agree on the unit ball. So in order to do this, we multiply by a function h that's supported on the unit ball, and instead of looking at the Fourier transform of the gradient of big F, which is equivalent to the expression in the Barron constant, we look at the Fourier transform of the gradient of f times h. Since we know that big F has to agree with little f on the unit ball, this quantity is going to be the same regardless of which extension we choose. And we can relate this back to the original integral using Young's inequality. And so we get this theorem, which gives a way to certify a lower bound for the Barron constant by choosing a function h and then computing this ratio. And for our purposes, we will choose h to be a certain bump function, and then several pages of Fourier analysis will finish the proof. Okay, so finally, I'll give some future directions for research. So one of the holy grails of neural networks is to try and separate the power of L and L+1 layer neural networks. And there has been a lot of some promising work in this direction. it will be interesting to have easily checkable, either sufficient or necessary conditions for some non-trivial family of functions. And another open question is to give a separation between the power of shallow and deep neural networks to express distributions. We only have looked at expressibility by functions here. Second, I'm interested in provable algorithms for learning neural networks. People have used tensor methods and kernel space methods. And in some sense, the kernel space methods can be thought as inspired by Barron's theorem. Just instead of using a L1 norm, you have a kind of L2 norm instead, which covers some little different set of functions. So one can also think about Barron's theorem as giving this convex relaxation, but in this infinite dimensional space of functions. Is there some way that we could take advantage of that? Finally, it'll be interesting to see if there's analogous results for probabilistic neural networks, such as RBMs. Is there also some kind of Fourier criteria for representability? Okay, so in conclusion, we initiated the study of what distributions can be represented by neural networks. We extended Barron's theorem to multi-layer neural networks, and we showed a separation between Barron functions and composition of Barron functions, analogous to a separation between 2- and 3-layer neural networks. And feel free to contact me to continue the discussion. Thank you. That's true. So the weights don't have you. There is if you can bound the weights if you wanted to with more complicated proof. Not too big. No.
So, do you have any, especially in terms of separation, do you have any result about necessity of the variant function, being a variant function, or is it representable very necessary?
So technically, you don't quite have a necessary condition because somehow the order of quantifiers is a little doesn't quite give you the full strength of a necessary condition.
When you collapse the internal state, how can you be sure that the number of output states is the same as the number of input states as the next layer?
Oh yeah, so the number.
You didn't see an hypothesis of the size of the outputs?
Yes, so each fi is a function from r to the mi minus 1 to r to the mi, and then mi is going to be the number of nodes there. So that's already set by the functions that you had.